Okay, so last time we went over up to here. So today we're gonna finish up by covering spectra. Now, an emission spectra or emission spectrum basically just shows the specific colors or wavelengths that specific elements are able to emit. So if you look here, we have hydrogen, and hydrogen emits these 4 specific wavelengths, whereas helium will emit a different amount or different types of wavelengths. So over here, you can see helium's emission spectra, and basically each element will have its own unique emission spectrum. And this is really useful because you can use specific, you can use the element spectrums or spectra to figure out what elements are within a certain substance. So scientists will often use this when looking at stars to figure out how old they are. So depending on the age of the star will have different elements. So what they're going to do is they're going to find or figure out the spectrum of the star, and then they're going to match it up with the spectra of different elements, and whichever lines match up, then you know that that element is in that star. So if you look here, I'm going to do star 1, and then you guys will do star 2. So if you look at star 1, you can see that I'm just going to go down these elements to see which elements are in this star. So if you look at calcium, you can see that this line matches up with star 1's. And just to double check, I can look at the other lines as well. So let's look at like this line right here. You can see that it matches up with star 1's. So all the lines, if your element or if your star has that specific element, then all the lines of the spectrum should match up. So again, even here, you can see it matches up. So star 1 definitely has calcium. And then we can check hydrogen. So hydrogen, it has 2 of these lines right here. And it matches up with star 1 as well. So calcium and hydrogen are present. And then let's check iron. So iron, you just look for like distinctive bands. So right here, it seems like it has a really dark band right here, but it's not present in star 1. And we can even check like other bands too. So like right here, it has a very dark band, but it's not really present. There's like a faint band, but it's like a little bit off. And then even with magnesium as well, magnesium has this very light band and a dark band right here, but it's not really present in star 1. So star 1 would only have calcium and hydrogen. And now this one is like a little bit, I don't know, it might be like, because it has so many lines, it's kind of hard to tell sometimes. But star 2 should be a lot more straightforward. So take this poll, and then while you guys do that, I'm gonna take attendance. Okay, so let's go over this. So for star 2, again, just match up the elements. So calcium is definitely not present. And then hydrogen, if we look, the bands match up here. So it definitely has hydrogen. And then iron, if you look, these are not present in star 2, right? All these bands here, they're not really present. Even these ones right here, not present. So it doesn't have iron. And then lastly, magnesium matches up. So maybe you got confused because maybe you thought, okay, well, it has this band here. So maybe this band matches up the one from iron. But again, if the element is present, all the bands of that specific element are going to show up. So like all these bands right here for iron, you can see that the lines don't show up in star 2. So iron can't be present. So you would have hydrogen and magnesium for this star. And then number 2, each line in the spectra represents the energy. So remember, the lines in the spectra are represented by the energy that the electrons are emitting. And remember, electrons emit energy when they're released, when the energy is released as the electron moves from higher to lower energy states. So this was kind of like a review. So the correct answer should be D. energy is released as an electron moves from higher to lower energy. Okay, so let's move on to the actual lesson for today. So today we're going over elements on the periodic table. And we're basically going to see how to predict the reactivity of certain elements. And first thing that we're going to do is we're going to compare sodium and neon. And the reason why we're going to do that is because if you look at sodium and neon, give me a second. Okay, so if you look at sodium and neon, you can see they're kind of on like the opposite sides of the periodic table. So it'll give us a pretty good indication of how these elements will behave. So we're going to compare sodium and neon by adding it to water and seeing what happens. So if you look and you add neon, you can see that you're just going to connect it to a tube of water. And there's like bubbles that rise, but nothing really like happens. And then if you add sodium metal, you can see you have like kind of a big explosion. So I'm going to show one more thing. Just give me a second. Okay, so this person here is going to add a big chunk of this sodium metal into a lake, and you can kind of see what happens. And also, if you notice, sodium, it's not the same type of sodium like in your table salt. That's sodium chloride. So this is pure sodium metal. So you can see he's going to toss it up into the air. And you'll see it starts to fizz automatically, catches on fire, and then explodes, right? So you can see that again. So you can see that sodium is a lot more reactive than neon was. So I'm gonna have you guys take another poll and then we'll go over it. Okay, so obviously sodium is in that first column, so it has one valence electron. Okay, and then neon is in the last column, so group 18 has 8 valence electrons. So 1 valence electron, 8 valence electrons, and then based on our observations, helium or hydrogen. So you should kind of know this, right? Like you fill up your balloons with helium, so obviously helium can't be dangerous, and it's in that same column as neon. So most likely helium would be one that's not, or that's going to be safer than filling with hydrogen. And you can see here as well. So let's say you fill a balloon with hydrogen or a blimp with hydrogen. It's going to be pretty reactive because it's in that same group as helium. And you can see this hydrogen blimp was one caught on fire and exploded. So, based on your result, you can kind of see that like one is very reactive, like hydrogen and sodium. So today we're going over these different groups on the periodic table. The first group we're going to go over are the noble gases. Now, the noble gases, there's a lot of words here, but I'm just going to kind of highlight what's the most important things about these groups. So the noble gases are not very reactive. They're the least reactive elements on the periodic table. And these are all in group 18. So these are your noble gases. Now, the reason why they're so unreactive is because they have something called a full octet. So a full octet means you have 8 valence electrons. Or it could also just mean like you have a full valence shell. So it means your outer shell of electrons is filled. Obviously helium, noble gas, but it only has 2 valence electrons, but it's still considered a full valence shell because remember that first layer of electrons can only contain up to 2 electrons, so it's still filled. But basically, this is why noble gases are so unreactive, is because they have that full valence shell of electrons. And all elements always try to get a full valence shell. So they're going to react with different elements to try to get that full valence shell. But if you already have a full valence shell, then obviously you're not going to react at all. Okay, so noble gases, most unreactive elements on the periodic table. Okay, so on your periodic table, you have metals, nonmetals, and metalloids. So different types of substances on your periodic table, and your periodic table is basically split up into these 3 types of substances. So metals will generally be on the left, and you can see they're in green, and then nonmetals will be towards the right, and then metalloids will be kind of like this center section. So you should know like what a metal is. Just think of the generic metals that you know of. So like gold or silver or aluminum. So they're good conductors of heat and electricity, and they're very malleable so that you can like bend them without breaking them. And nonmetals are basically going to be everything that a metal is not. So like your gases or brittle solids like sulfur. And then your metalloids are going to be kind of a hybrid between these 2 substances. And the only nonmetal that exists on the metal side of the periodic table is hydrogen, because hydrogen is a gas. So basically all the nonmetals besides hydrogen will be over here on the right. So that transitions into our next group, which is group 1. And group 1, this is known as the alkali metals. And alkali metals are unique because they're the most, or one of the most reactive groups on the periodic table. So you can see they're very highly reactive. And the reason why they're so reactive is because they only have 1 valence electron. So if we look over here at these Bohr models, these are all the Bohr models of the alkali metals. And you can see that they're only 1 valence electron away from obtaining a full valence shell of electrons. So what does that mean? Right? So all of these alkali metals, if you just removed 1 electron, then you would move back down to the previous layer, and now you would have a complete set of electrons. You would have a full valence shell. I guess technically what you could do is you could add 7 electrons instead to fill that valence shell, but that's a lot more difficult to do than just removing 1, right? Because if we just remove 1, then we'll have a full valence shell in the previous layer. But if you add 7, you could also have a full valence shell, but it's going to take forever, or it's going to be hard for that element to find 7 electrons. So alkali metals, what they'll always do is they'll always give away 1 electron to have a full valence shell. So you can see, right, all of these, if you just take away 1 electron, it'll have that full valence shell. And that's why they're so reactive. It's because you only have to give away 1 electron, which is not that very difficult to do. So alkali metals, one of the most reactive groups on the periodic table. Now, the next group on the periodic table are known as your alkaline earth metals. This is group 2. And a difference between the alkaline earth metals and the alkali metals are that the alkaline earth metals are harder than the alkali metals. And how I kind of remember this is alkaline earth metals, calcium belongs to that group. And calcium is like what's used to make your bones strong. So everything in the alkaline earth metals group will be a harder metal than the alkaline metals. But the most important thing about the alkaline earth metals are that they are reactive, but not as reactive as the alkaline metals. Okay, so they're still reactive, just not as reactive. And the reason for that is because alkaline earth metals, they're less reactive than alkaline metals because they have to lose 2 valence electrons, whereas your alkaline metals only have to lose 1 valence electron. So again, you can see here, right? These are all your, these are 3 alkaline earth metals. And to get a full valence shell, or to move down to that first, or to the preceding layer of full valence electrons, for beryllium over here, if we just lose these 2 electrons, then it'll have a full valence shell. Same thing with magnesium here. Let's lose these 2 electrons and you'll have a full valence shell, and then same thing with calcium. So all these alkaline earth metals will behave the same way. Lose 2 valence electrons to get a full valence shell. Okay, so I'm gonna have you guys take this next poll. And then we'll continue on. Okay, so let's go over these questions. First question, why are elements in the noble gases gas family not reactive? So again, that's because the noble gases, they have the most valence electrons. So they're gonna have that full outer shell. Next, which element would act most like sodium? So it'd be whatever is in the same column or same family as the alkali metals. So that would be potassium. Next, which would you expect to be more reactive? So lithium or beryllium. So you would choose whichever one is the alkali metals. So if you look over here, lithium is in the alkali metals, which are more reactive than beryllium because they're closer to a full valence shell. So lithium would be the most reactive. And then which metal do you expect to be harder? That would be whichever one is your alkaline earth metal. So in this case, it should be magnesium, not potassium. So magnesium would be the harder metal. Okay. So moving on, we're going to talk about elements that you should be kind of familiar with, and that's your halogens. So halogens, I guess the most famous one would be chlorine, which is used to clean your pool. And the most important thing about your halogens are they contain 7 valence electrons because they're in group 17. And they're really good at cleaning things because they're very reactive. So a lot of times they're used as like disinfectants. So chlorine or even like fluorine or fluoride in your toothpaste. Iodine can be used to make dirty water safe to drink. So these are all very reactive elements. And basically halogens and your alkali metals are the most reactive elements. And the reason why halogens are so reactive is because since they have 7 valence electrons, they only need to gain 1 more valence electron to complete their valence shell or their outer shell. So you can see here, right, all of these have 7 valence electrons. So for fluorine, if you just add 1 more electron, then it'll have 8 valence electrons. Same thing with chlorine, bromine, iodine, they all behave the same way. And I guess you could technically, like, to get a full valence shell, you could just take away 7 electrons, but like before, this is way more difficult to do than just adding 1. So for halogens, you'll just always add 1 more or gain 1 more electron to complete that valence shell. Okay, so those are kind of like the main groups of elements that we're talking about today. The rest are, I'm just going to tell you kind of what their names are, but you don't have to worry too much about them. So transition metals are the metals that are in this block in the middle of the periodic table. And they're basically like the typical metals that you think of. So like titanium, iron, copper, silver, they're all going to be located here. So they're not like unique in the sense where they're going to explode out of nowhere, like these elements over here. And they just have characteristics that are very, I guess, predictable. So they're very hard, they're very conductive, so they transfer heat and electricity well. They have high melting and boiling points, and these are all here. And then next we have our lanthanides and actinides. So that's in this bottom two rows over here. And these elements actually belong kind of inserted in here, but that would make the periodic table too wide. So they just like put them off separately here. But you can see, right, lanthanides and actinides. So if it goes from 56, 57, and then it would go to 58, 59, 60, etc., 71, and then back to 72. So they fit in perfectly right here. So this first row, these are your lanthanides. These are your actinides. And you don't really need to worry too much about these or what they do. If you really want to know, your actinides are your radioactive elements. So they're like, for example, uranium and plutonium. Those are kind of used for like nuclear power plants. And then lanthanides are conductive elements. And they're a lot of times used for like high technology. So for example, ND is used to make magnets for electric and hybrid cars, or like ER is used for lasers, for laser surgery and optical cables. But again, don't worry too much about these. Okay, and then the last part of the lesson is we're going to talk about ions again. So remember, ions are atoms that have gained or lost electrons. So they're going to have a positive or a negative charge. So cations are the names for your positive ions, and anions is the name for your negative ions. And how you memorize this is anion literally means a negative ion, right? A-N-I-O-N, anion. And then cation, some people, if this helps you, you could use it like cats are positive, so cations are positive. If that helps you, go ahead and use that. So you have your anions and your cations, and basically all of your elements on the periodic table are going to tend to either form anions or cations. Obviously, there's some exceptions, but most of the time, it's either just going to form a cation or it's going to form an anion. So generally speaking, your metals, so everything to kind of like the left of the periodic table plus hydrogen are going to form cations. And then your nonmetals over here are going to form anions. So this is generally speaking. And the reason for that is based, again, of that idea that we've been talking about, where elements want to gain a full valence shell. So you can see here, your noble gases are going to remain neutral elements because they don't need to gain or lose electrons. So they're never going to react with anything. And since they're never going to react with anything, they're going to stay neutral. But all your other elements tend to either give or take away electrons. So you can see here, right? Like, let's say if we look at lithium, if we drew out the Bohr model, you can see, like we've been talking about, lithium will want to lose one valence electron. So since it loses a valence electron, now it has a full valence shell. But since it lost an electron, it would have a +1 charge. So this is kind of going back to calculating net charge from your previous lessons. Or like fluorine, if you look. So if I draw out fluorine, 1, 2, 3, 4, 5, 6, 7, it only needs to gain one more electron to get that full valence shell, which means it would now have a -1 charge because it added an electron or gained an electron. Okay, so let's go over these examples. It says if beryllium gained or lost electrons, how many electrons would it gain or lose? So again, there's two ways to kind of do this. One way is to draw the Bohr model. So if I draw the Bohr model, you can see it seems easier for beryllium to just lose these 2 electrons than to gain 6. So if it loses 2 electrons, then it would obtain a full octet. Okay, so again, all your elements will always want to gain a full octet. So let's take this last poll. I already did the first question for you. So you do the ones for nitrogen and for bromine. Okay, and then I'm gonna actually show you the periodic table because it's kind of hard to do it without that. Okay, so let's finish this up. Okay, so next example for nitrogen, I'm gonna do over here. So nitrogen, again, if I just draw out the Bohr model, it would have 5 valence electrons. So to gain a full octet, you would need to add 3 more electrons. So add 3 electrons. Okay, and that would give it, so if you add 3 electrons, then that would make it -3 charge, or an anion, right? And you can see that matches up with what it says right here. Nitrogen will want a -3 charge. Okay, and then you could do the same thing for bromine. And bromine has like a lot of electrons, so you don't technically like have to just draw out all of them. But let's say I just draw out how many rings it has. So it has 1, 2, 3, 1, 2, 3, and then here. Let me make a better picture. 1, 2, 3. So it has 4 rings. And then I can just draw out the valence electrons that bromine has in that 4th ring. So bromine is in group 17. So it has 7 valence electrons. So I know it has 1, 2, 3, 4, 5, 6, 7 valence electrons. So to get a full valence shell, you would just need to add 1 more electron. So gain 1 electron. And then if you gain an electron, that means you're going to have a -1 charge, which means you would be an anion. And again, you can see that matches up with this here, right? Bromine is in this column, and it has a -1 charge. So again, your metals will all tend to gain, your metals will gain electrons, lose electrons. And then your nonmetals will all tend to gain electrons because all these elements over here, they have few valence electrons, so it's easier for them to lose it to move down to the next valence shell. But then these over here, they have a lot of valence electrons, so it's just easier for them to gain an extra electron and get that full valence shell. Okay, and that's pretty much it for today. So finish the lecture and the quiz, and then you guys will be good for the weekend. Okay, if you have questions, you can stick around. Otherwise, you guys are good to go. Bye, everyone. I'll see you guys all next week.